We're now going to explore the impact of lambda as a value and see how it ties into these calculations. We're going to recompute the optimum values of W and K when we have an extra budget dollar. So what we're going to have is the same function, W to the 3/4, K to the 1/4, and we're now going to have the budget constraint, exactly the same thing, $10 per worker, $20 per capital, and instead of 3,200 though, we're going to have 3,201. Now the nice thing about that is we went through some analysis of this function here, and that's going to be identical. And that led us down to two equations, which was 3K over W equals 1/2, or we ended up with 6K is equal to W. So that was an equation we got without ever referring to the constraint. So we can use that with a new constraint and see where it gets us. We call that equation 4, we call that equation 3. Now we'll put 4 into 3. And once we do that, we're going to have 10 times 6K plus 20K equals 3,201. So 80K equals 3,201. And so K is going to be 240, like before, plus, what else are we going to get? Sorry, it's going to be 40, plus a little fraction, 1 over 80. Because we put in 40, 80 goes into this number 40 times, and there's a 1 left over. So it's nice to highlight the contrast or the effect of this change in budget. Our workers would be 240 plus 6 over 80. That's coming from our 6 times K. Okay. So what does that tell us? Well, it tells us that when we increase our budget, we're going to have a certain corresponding increase in the capital we can spend and the number of workers we can hire. Our next step is to look at the actual production effect of this extra dollar. So we just spent one more dollar. We broke it up in this way to spend it between capital and workers. And what we can say is that our old Q, which was that 240 workers and 40 units of capital, we could plug that value into our formula for the number of units produced, and we would get 920.078. If we do our new Q, which is at 240 workers plus the 6 over 80, so a little increase in workers and 40 units plus an 80th of capital, we get almost the same productivity. Not too surprising. We wouldn't expect $1 more to get us a whole lot more in production. But we do get a change in productivity here. We get a delta Q of around 0.29 for that impact. Okay. So far, nothing too deep going on here. We change our budget. We get a different distribution for the optimum values. Where would we get this number maybe a little more easily? Because this is a lot of work just to get the impact of one more dollar. We had to resolve this equation, resolve these equations, plug it back in. Well, if we take a look at, say for example, our partial derivative relationship for the, let's use the capital equation rather than the workers. Here we had 6 W to the 3/4 and times 1/4 capital to the negative 3/4. That was equal to lambda, and the derivative with respect to capital was 20, the price of each unit. And if we solve for lambda, again at, let's say 40 workers, 240 workers and 40 capital, we're going to get that lambda is equal to 0.288. These numbers, again, now they're not coincidence, these two numbers are almost identical, and this is the instantaneous rate, this is the average over $1, but the idea here is that lambda is approximately the effect on F of a $1 increase in budget. That's the easiest way to think of these kinds of models. We can think of an input in the budget or an increase in the constraint value. In this particular case, it is a budget, so it makes perfect sense to talk about $1. Usually we just say 1 unit of the constraint value. But what that gives us is, if we can find lambda, we can find the impact of changing our constraint from 3200 to 3201, or we'd expect twice as much if we went to 3202. It's quite a powerful tool for quickly estimating the impact of modifying our constraint. Last but not least, we'll just do a quick graphical analysis of the scenario here. This black line is the line 10W plus 20K equals 3200. So it's a nice negative slope. We have our workers down here and our capital up here. And we can see that the contour lines get higher as we move towards the upper and right. And so if we were looking for following this path and ask when are we going to reach the possible highest value, well, it's going to be probably in this range here. We can hit 800 here, we can hit 800 over here. Somewhere in the middle, we're probably up to about 9. Oh wait, we already calculated this. About 920 is where we expect to be able to reach. So let's take a look a little more zoomed in. Notice the 240 and the 40 for our workers and capital. That's where we found our optimum. Scan up here. There we go. That's where our constraint line, we're only allowed to pick things that match our budget. Just touches this 920 contour, it just comes in, just touches it there, and then diverges off. And so we get our classic gradient calculation there, where the perpendicular line, the gradient on the contour lines, is going to equal or be parallel to, it's going to be parallel to the line perpendicular to our constraint. And we can also see the change in budget that we get. This is if we move our budget up $1, delta budget equals 1. We can see the move between that and up to the next contour line over almost. And that gives us an estimate of the impact between these two lines here of lambda, or the delta F. There's really more delta F there. So we can start to get some visualization of all the calculations we did throughout this example.